Welcome to this session on AWS ParellelCluster. My name is Nathan Stornetta, and I'm a product manager at AWS for HPC products. In this session, I'll be focused on introducing you to the tools and ideas that you need to be able to run your high-performance computing or HPC workloads on AWS with ParellelCluster, an orchestration tool that we make available at no cost to our customers. The agenda that I'm going to be following in this session today is going to be as follows. First, I'll provide a brief overview of HPC on AWS, what it is that makes it compelling to customers, what our portfolio of AWS services for HPC looks like, as well as a few cases in which our customers have been successful running their HPC workloads on AWS. Next, I'll spend a little bit of time introducing AWS ParellelCluster, an essential product in AWS's HPC portfolio that makes it fast and easy to set up HPC clusters in the cloud. After that, I'll go through a live demo. I'll show you what it looks like to configure and run a couple of different HPC clusters, as well as showcase some of the newest features that we have to offer within ParellelCluster. To understand the value of AWS ParellelCluster, it's worthwhile to first understand why it is that AWS is ideally positioned for running your HPC workloads. With this, one of the biggest benefits that we offer is the ability for our customers to work elastically with our virtually unlimited infrastructure. That elastic capacity means the ability to scale up quickly and on demand, paying only for the resources that you use. That stands in sharp contrast to working with on-prem HPC, where you are necessarily constrained by your finite capacity. In practice, for on-premises HPC, that results in resources that are either shared across many users and jobs that are bin packed as tightly as possible. That leaves your users waiting in long queues for their jobs to run, as well as having to run workloads on general purpose servers rather than using clusters that are specialized to each and every one of your workloads. Running your HPC on AWS removes these constraints. With AWS, the quantity and type of infrastructure you can use is dictated by what you need in the precise moment you need it, as you scale up and down elastically to meet your business or research needs. And these benefits are far from theoretical. Formula One elected to use AWS to design its next generation race car. Formula One uses computational fluid dynamics to simulate the aerodynamics of their race cars and understand how it is that different designs affect the ability of their vehicles to race in close proximity to one another. That results in more exciting wheel-to-wheel racing with faster cornering speed. Running on AWS using ParellelCluster and AWS's proprietary network interface called Elastic Fabric Adapter, or EFA, they were able to reduce the runtime of their simulations by 70%. That gives them time to test more ideas and ultimately produce the racing events that are more exciting every year. Likewise, Maxar, a technology company delivering the fastest possible weather forecasts to its customers, who need the most up-to-date information on weather and how it could affect their businesses, chose to run on AWS because they knew it could help them run their on-demand workloads at a moment's notice, all while achieving top-notch compute performance. Using AWS ParellelCluster, EFA, and AWS's own high-performance managed file system, Amazon FSx for Lustre, Maxar found they could spin up exceptionally high-performance compute environments at a moment's notice. With this infrastructure, they computed forecasts 58% faster than the dedicated weather supercomputer operated by the National Oceanic and Atmospheric Administration, or NOAA. And because Maxar only needs to run their workloads for an hour or so per day, they have been able to realize significant cost savings versus having always-on infrastructure. As you can already tell from those examples, there are a number of tools that go into helping our customers achieve the best performance and cost savings possible on AWS. From our specialized compute instances, including Graviton2 instances that use an ARM-based architecture, our own network interface, Elastic Fabric Adapter, our high-performance file system, Amazon FSx for Lustre, and the tool I'll be talking the most about today, AWS ParellelCluster. AWS ParellelCluster is our open source tool for connecting the different components that we offer for HPC on AWS and helping you orchestrate all of your HPC workloads in the cloud, even if you're unfamiliar with each of these different tools. At a high level, ParellelCluster is an open source cluster management tool that's managed primarily through a command line interface, or CLI. Here, when I say cluster, I'm referring to a system with a head node, compute nodes, a job scheduler, and a shared file system. Three of the key benefits we've seen for customers using ParellelCluster is that it makes cluster management easy, it includes automatic resource scaling, and it facilitates a seamless customer experience in migrating HPC workloads from on-premises environments to the cloud. This makes it a great choice for all kinds of HPC, from spinning up a quick test cluster to fully migrating all of your HPC workloads. The basic workflow for ParellelCluster has 3 core steps to make cluster management simple and easy to organize. Get started with the configuration wizard to streamline the definition of your cluster. Next, you can further customize detailed specifications for your cluster, or create multiple variations on your cluster using text configuration files that are easy to maintain and give you close control over the wealth of options you have with AWS. You can store and manage these configuration files locally on your own machine and stay organized to track any number of clusters you wish. Finally, once you have everything set up just the way you like it, you can start, stop, restart, and check the status of any one or all of your clusters using the same ParellelCluster command line interface. We've designed ParellelCluster with elasticity firmly in mind, and you can easily take full advantage of this flexibility without any extra work on your part. When you submit a job, ParellelCluster will automatically scale up the resources that you need. If you submit more than one job, ParellelCluster will continue scaling up more resources to match those additional jobs too. This automatic resource scaling eliminates the need to wait for computing resources to become available. On the other hand, since you may not need to be running jobs 24/7, ParellelCluster will scale down for you when computing nodes are idle. When individual nodes have finished running their jobs, ParellelCluster can take those nodes offline in a safe way, so that you only end up using the resources you need when you need them, saving you money and keeping you from having to manually start and stop your cluster all the time. This elasticity applies to your data storage and file systems shared across all of your computing clusters as well. With the virtually unlimited infrastructure in AWS, you can bring even your largest data to AWS and use it in a performant and cost-effective way for HPC. Another reason customers love ParellelCluster is that it makes migrating existing workloads to the cloud easier. Because the cloud is a radical departure in many ways from traditional on-premise environments, that means lots of applications can benefit both in terms of performance and cost effectiveness by re-architecting workloads with a cloud-native approach. Making that transition is part of an overall process, however, and that can take some time and planning. ParellelCluster provides an environment and tools that are already familiar to HPC users, simplifying your first steps in this migration process and making it easier to lift and shift your workloads to the cloud with only minimal adjustments. You can pick and choose which workloads you're ready to move to the cloud and do it at your own pace. And what's great about ParellelCluster is that because it integrates with so many other AWS products, you can transition to using more and more cloud-native services when you're ready from the workloads that you already have migrated with ParellelCluster. So when you're ready to make some or all of your HPC workloads cloud-native, ParellelCluster is ready to help with that too, giving you a chance to get easier or more cost-effective performance than you otherwise could. As an HPC orchestration tool, ParellelCluster makes it easy to take all of the disparate and sometimes messy pieces in the HPC ecosystem and organize them into a nice package that's both flexible and easy to use. That includes everything from your operating system, your job scheduler, your choice of shared file system, your choice of data storage, your choice of networking configurations, and your MPI or collective communications libraries. That's before even considering the wealth of options you have available in your choice of compute nodes. And again, all of these options are accessible through the ParellelCluster guided configuration and the easy to use and manage configuration files that dictate your cluster's architecture. Taken together, all of these different benefits can make ParellelCluster the best choice for HPC on AWS for a number of different use cases. ParellelCluster makes it easy to take production workloads and focus on optimizing them so they can run faster or with greater precision, thanks to the fact that you can customize your infrastructure for each and every type of job you want to run. Fast prototyping is likewise easy with ParellelCluster because it makes the elasticity of AWS so accessible and lets researchers or engineers test new products or experiments quickly and on demand. Similarly, something else we've heard from customers that they love about using ParellelCluster is that it lets them run workloads on short notice when there are specific business needs that demand it. And so when they need to finish that job today in order to meet a business critical deadline, they don't have to worry about finding space in their on-premise environment or figuring out how to set up their cluster in the cloud by themselves. Because of its flexibility and depth, we've seen customers across a wide number of industries find success in using ParellelCluster. That includes life sciences, where customers have run applications ranging from drug discovery, genomics, and cancer research. Financial services, where we have customers running financial risk simulations and quantitative trading algorithms. Oil and gas, with customers running reservoir modeling and seismic imaging. Design and engineering, with computer-aided engineering and computational fluid dynamics. And even climate and geosciences with weather forecasting and climate modeling. We've even seen a number of customers adopt ParellelCluster as the orchestration layer for the distributed machine learning and deep learning workloads, such as using applications like PyTorch. Regardless of your industry vertical or the nature of your precise workload, ParellelCluster can make the infrastructure needed to run them accessible and performant. In 2020, we've come up with a number of additional feature enhancements for ParellelCluster that we think are going to be really interesting to all of our customers. That includes the ability to configure multiple job submission queues, the ability to use multiple instance types in each one of your job queue, as well as the ability to use our latest AWS Graviton2 compute instances like C6G and M6G to deliver some of the best price performance that AWS has to offer. I'll be going over some of these different features in a live demo. To start, I'll show you how easy it is to install ParellelCluster and get up and running for the first time by using the pcluster configuration wizard. If you wanted to install ParellelCluster for the first time, you can do so using the pip package manager, like so. In my case, I already have this installed. We have access to a number of different options that we can use from our terminal or command line interface to configure our clusters, as well as to manage and deploy them. To start, I'll show you just briefly how it is that you can configure a cluster using the pcluster configure command. Here, this guided configuration wizard will take you through some of the key steps that you need to define your infrastructure for your cluster, such as the region in which you want to deploy your cluster, the EC2 key pair that you need to use in order to access your cluster, the job scheduler that you want to use to submit jobs once your cluster is up and running, the operating system you want to use, as well as the number of instances that you want to be able to scale up and down to dynamically. Here, we can set the minimum cluster size, the minimum number of compute nodes that we would have. I'll set that at 0. The maximum number of instances that you want to be able to scale up to, as well as the instance types for both your head node as well as your different compute nodes. Here, I'll just leave these as the default, which is a T2.micro. And then you can choose to automate your VPC creation, which will help ParellelCluster define your networking setup in a way that keeps you from having to define that yourself or go through some of those nitty-gritty details. Once you've done that, you can take a look at your configuration file. In this case, it's stored in the default location inside of the ParellelCluster directory. And you can see how each of these different options that we chose during the configuration wizard process have now shown up inside of our text file. Once you're ready to actually go ahead and deploy your cluster, it's as simple as just running the pcluster create command. In this case, we won't wait for the cluster to create. It takes just a couple of minutes. I've already created a cluster for us to take a look at. Once your cluster is ready and deployed, you can log into the head node of your cluster by using the pcluster SSH command and supplying your key pair. I forgot to include my cluster name, so I'll fix that real quick. And as you can see, now I'm logged in to my own ParellelCluster cluster. And at this point, I could go ahead and I could submit, I could use the Slurm job scheduler to go ahead and submit a job. This is just a simple hello world job that I have here. And we can see how it is that ParellelCluster has helped me submit that job. And it's now going to be running on this resource right here, this node. If I prefer not to use, not to SSH directly into the head node, I also have the option of using DCV to open up a graphical remote desktop interface into my cluster, which I can do like so. Once I've run the DCV command, now I can open up my desktop interface through a browser, and I can have visual access to all of my directories, as well as be able to open a command line if I wish to submit jobs directly from there. Being able to use DCV also gives you the option where you can use this for post-processing visualization, for example, on something like computational fluid dynamics workloads, where you need to be able to see and visualize the outputs of your jobs and interact with them directly. Like I mentioned before, with our latest release of ParellelCluster, it's also possible now to create multiple job submission queues, as well as to create job submission queues that have access to multiple instance types simultaneously. I'm going to show you quickly just how it is that you can convert an already existing configuration file like the one we created before, so that it can take advantage of this multiple instance queue and multiple instance type functionality. I'm going to take a brief look just at an example configuration file that I've made before with access to a single queue, as you can see here. This looks basically like the configuration file that we created previously. And how it is that we can first convert that into a multi-queue configuration file using the ParellelCluster command line interface. We can do that like so. Using the pcluster config convert command, specifying the file that we want to convert, and then specifying where it is that we want to put our new file. Oops. Try that again. And now taking a look at that file, we can see that our file has been modified so that it includes these new section settings, queue and compute resource, that give us the flexibility to define more than one instance type, as well as more than one job submission queue. I'll show you just a little bit more how these settings work, as well as talk you through some use cases for how you might use those options. A common setup inside many traditional HPC environments is to use multiple queues that have varying levels of priority and different compute resources associated with them. That can help ensure that the most urgent workloads have prioritized access to resources they require, while other workloads can wait longer or run on resources that have lower costs. While AWS offers additional scale beyond what traditional on-prem environments can offer, so you don't have to queue up or prioritize your jobs, you can apply a similar framework using EC2 On Demand and EC2 Spot. For important workloads where time to results matter, or where you might be unwilling to tolerate interruptions to your compute resources, you can set up an AWS ParellelCluster job queue that uses EC2 On Demand. For low priority workloads where you are able to tolerate interruptions to your capacity, or you're willing to make multiple requests to see if excess EC2 capacity is available, you can set up an AWS ParellelCluster job queue that uses EC2 Spot. As you can see here, in this multi-queue configuration file, I've gone ahead and I've specified that I want to use multiple queues, in this case labeled OD, or on-demand queue, and Spot queue. And then I've separately defined the characteristics of each of those different queues inside of their respective queue settings sections. Here, I define the Spot queue settings, where I can apply settings such as the ability to enable Elastic Fabric Adapter, or EFA. I can disable hyperthreading. And then I can define what kind of compute resources I want this queue to have access to. I've done the same thing here, as you can see, with the on-demand queue that I've defined separately. In each of these cases, I've defined the compute resources for the Spot C5N compute resources and the on-demand C5N compute resources here, defining the instance types, in this case, a C5N 18x large, as well as the minimum number of instances and the maximum number of instances that I want to be able to scale down or scale up to. In addition to being able to define multiple job submission queues, we can also define different compute resources within or across multiple different queues. In this case, I've created a configuration file that allows me to access and use multiple different Graviton instance types. In this case, you can see that my configuration is relatively similar to the previous one I just showed you, except I'm using just a single job submission queue, in this case labeled compute, but I'm defining multiple compute resources within that job submission queue, in this case C6G and M6G, each of them defined in their own sections here. This allows me to have access to more than one instance type if I wish to be able to run different workloads that require different compute characteristics with each one. If we SSH into the cluster, as I'll show you in just a second, we also have a way of ensuring that when we submit a job, it's running only on the instance type that we want when we require that level of specificity. Switching back into the terminal, we can go ahead and we can log into our cluster. Once we're here, we can see the compute resources that we have access to. And we can go ahead and we can submit our first Hello World job. And we can see that that by using the sbatch command, we've gone ahead, we've invoked this hello world job, and automatically ParellelCluster is starting to spin up the resources that are required to run that job. Next, I'm going to show you how it is that in addition to being able to specify the cluster configuration before cluster creation, we can actually go ahead and use the pcluster update command to modify the characteristics of a running cluster. And I'll show you how we can do that like so. Make sure that I've got the right config file here. Okay. So here I can use the pcluster update command, specify the configuration file that I want to reflect the updated state of the cluster, and then include the cluster name. And ParellelCluster will go ahead and it will analyze the differences between the running cluster and the desired cluster configuration. And go and help us understand how it is that we can, what changes are being made, as well as how we can execute those changes. In this case, it's telling me that I need to go ahead and stop the running Graviton cluster. And that I can then rerun my command. In doing so, I'll be updating that cluster so that whereas it previously had only had the C6G instance type, it will now have the C6G and the M6G instance types that I'd specified in the configuration file that I showed just before. Yep. Looks like we still need to wait for the cluster to stop. And now the cluster is stopped. So we can go ahead and we can submit that update again. Like so. Leaving that aside for the moment, I'll go ahead and show you just as a final step how it is that you can use the multiple job submission queues that you've created within a cluster and specify which of those queues you want to use using Slurm. So right now, I'll go ahead and SSH into a different cluster that I've created. And you can see here that I have these two separate partitions or two separate job submission queues, the on-demand queue and the spot queue. And just like before, I'm going to go ahead and I'm going to run the hello world job. But in this case, I'm going to be very specific and tell Slurm exactly which queue it is that I want to run this job from. So in this case, let's suppose first that I have a low priority job. And so I'm willing to run this on spot, subject to all of the limitations that come with that, and that there might not be excess capacity and that capacity could be interrupted. And we can see by looking at our Slurm queue that that job is successfully submitted, that it's running in the spot queue. Similarly, we could go ahead and do the same with our on-demand queue. And we can see as well here that that job has submitted separately to the on-demand queue using different resources from that queue. Finally, as a last part of the demo, I'll show you how it is that if you have multiple instance types in a single queue, you can go ahead and specify which of those instance types you want to use. Again, this can be done using Slurm, where you, in this case, will be using the constraint keyword. So here, I'll show you how it is that you can use the constraint keyword with Slurm if you wanted to specify a specific instance type within one of your job submission queues, say if you had more than one instance type. And that can be done like so. And we see now that by specifying this C518X large constraint, if we have multiple instance types in that single queue, we only use or apply that constraint to the instance types that we've specified. Okay. With that, you should have a taste for how it is that ParellelCluster works, as well as some of the latest features that we have to offer in terms of the multiple job submission queues and multiple instance types that can be configured within a single cluster. I hope you've liked what you've been able to see from ParellelCluster today, and that you can't wait to get started in running your HPC workloads in AWS. That's it for today. I hope you've enjoyed this look into AWS ParellelCluster and how it is that you can enhance your HPC workloads. Thanks for your time, and please let us know how we can improve this session.